So, going to go through the homework on alcohol that was set last week. First question, which statement about ethanol is correct? And it's the first option up there. It reacts with a Tollens reagent to form silver. Which compound can be oxidized to form CH32, CHCOCH3? That would be 3-methylbutane-2-ol. On number 3 here, it was quite common for people to say 60%. Hopefully that wasn't you. What you need to remember is percentage yield is what you got over what you should have got. And we need to be thinking about the moles and the mole ratios. So these ones react in a 1-to-1 ratio. So we know our starting mass. We know we had 50 grams of our propan-2-ol. So we know that we had 0.833 moles of that substance. And because of 1-to-1 ratio, we should have produced 0.833 moles of our propene. Now that wasn't the case, and you can see I've put the numbers in here. We actually made 0.714 moles. So into our percentage yield, I'm going to put 0.714 divided by 0.833 times by 100, and I get pretty close to 86%. So this question can look a bit daunting when we first see it, because there is a lot going on and we're looking at an ionic equation here. So propanol can be prepared by the oxidation of propan-1-ol with acidified potassium dichromate. And we're given the equation, and they ask us to calculate the minimum volume in centimetres cubed, so that's the unit that's going to be important, of 0.4 moles per decimetre cubed of potassium dichromate solution needed to oxidise 6 centimetre cube of propan-1-ol to propanol. And we're given the MR of propan-1-ol, and we're given the density of it too. And that's quite a good first hint about where to tackle this. So whenever we are looking at these type of equations, we'll think about how many moles do I have of one thing to work out how many moles you've got the other thing, so that you can work out volume or whatever it might be. So first step, we're going to work out the mass of propan-1-ol, and we're just going to take that volume and we're going to times it by the density, because that tells us how much propan-1-ol is in there, and that's 4.8 grams. Now we know a mass and we have an MR, we can work out the moles. So we have 0.08 moles of propan-1-ol. Nice and straightforward. Now, we've got to work out the moles of the dichromate ion. And we can see from the equation they're in a 3-to-1 ratio. So that means we need to divide our 0.08 by 3 to get the moles of the dichromate, which gives us a value of 0.0267. So now for the chromate ion, we know the moles and we know the concentration, so we can work out the volume. So volume equals moles divided by concentration. We plug those numbers in and we get an answer in decimetre cubed. Now remember the question was after centimetre cubed. So we need to convert those decimetre cubes to centimetre cubes by divide by 1000. That gives us a final volume of 66.67 centimetres cubed. Now for this one there is a lengthy mark scheme to go with it, but basically we're looking for you to draw the distillation equipment. But they're letting you get away with not having a thermometer or a collection container. They're more interested in the other glassware. You need to make sure that the condenser is attached to the side of the distillation head. You need to make sure there's no gaps between your bits of equipment, because otherwise things will escape. And you need to make sure you've got your water in and water out going in the right direction. So here is a sample diagram. Do look at your diagram that you've drawn, compare it to the one on the screen, and compare it carefully to the mark scheme. So this is a 5-mark question looking at ethanol, and we're told a dilute aqueous solution of ethanol can be produced by fermentation of an aqueous solution of glucose. It's claimed that ethanol obtained from this solution is carbon neutral biofuel. So the next list is things you need to do, and it's really common in these questions that people miss something out. So you need to write an equation for this fermentation reaction, give 2 other essential conditions for this reaction, name a process used to produce a much more concentrated solution, and state the meaning of the term carbon neutral in the context of biofuel. none of these things by themselves are complicated, but I think when we get these large blocks of text, people do often miss one of these things out. So let's go through those now. So our fermentation reaction is a nice straightforward one. We have got one reactant, which is our glucose, and that's going to form ethanol and some carbon dioxide. So there we go, we've got the formula there. And some conditions for this reaction to occur in. We need some yeast there, and we need warm temperatures, not too hot, not too cold. And we also need to make sure there is no oxygen there. But you only have to get 2 of those conditions to get the marks. Name the process used to produce more concentrated solution. That's distillation. And what do we mean by carbon neutral? It means that there's no overall carbon dioxide being emitted to the atmosphere. Or we could say there's no change in the net level of CO2 in the atmosphere. And that's because when the plant is being grown to make the glucose, it is removing CO2 from the atmosphere, and then later on that is being re-released again. So the net change is 0. So a bit of a wordy question here, and we need to find where the questions are within the text. A student carried out a lab experiment to determine enthalpy change when a sample of ethanol was burned, and the heat produced was used to warm some water, and they found that 75 grams of water increased by 5.5 degrees Celsius when 2.4 times 10 to the minus 3 moles of pure ethanol were burnt in air. So using their data, calculate an enthalpy change for 1 mole of ethanol being burnt, and they want this in kilojoules per mole, and then we need to give 2 reasons why our value might be different to the data book value. So step 1, we've got to think about which equation we're going to use, and we get credit for saying Q equals MC delta T. So that's your first mark, hopefully. Then we've got to plug the numbers in. So taking them straight from the student, we get 75 times 4.18 times 5.5, and that gives us an answer in joules. Now remember, we want this in kilojoules per mole, so I'm going to convert to kilojoules now by dividing by 1,000. Now, as we said, we want units of kilojoules per mole, so I'm going to divide by the number of moles that were burnt. So 1.72425 divided by our 2.4 times 10 to the minus 3 gives us 718.44 kilojoules per mole. Now we've got to remember this is an exothermic reaction, so we need to have a minus sign there to indicate it is exothermic. Finally, we were asked to give 2 reasons why the values might be different, and there are multiple reasons you could give. So any from, is it incomplete combustion, or the reaction isn't complete, not all the moles of ethanol were used. There's heat loss to the surrounding. We've not taken into account the heat capacity of the copper. Copper contained will absorb some of the energy, and some ethanol may be lost to evaporation too. So a nice straightforward definition question here, so hopefully a nice easy 2 marks. Give the meaning of the term mean bond enthalpy. So the mean there is a good clue. So we're looking at the enthalpy needed to break or dissociate a covalent bond. That gets you 1 mark, and that's averaged over that type of bond over many different types of molecules or compounds. So that will get you the 2 marks. Now, knowing that it's average is where they quite often ask another linked question where they might say, why is the CH bond in this structure different to the value in the table? And that's because it will be averaged, that CH bond, over many different molecules. So here we have a question about mean bond enthalpy, which hopefully you're starting to feel really confident about. You would have met it at GCSE, we now elevate it a little bit at A level. So we are asking something slightly different in this. We're working out the mean bond enthalpy for the O-double-O bond in the oxygen molecule, not the total enthalpy change. But it's a very similar method. Whenever doing these calculations, I would encourage you to draw out the structures. It makes it much easier when tallying. So let's look at the bonds which are broken first, which are all the bonds in our reactants. So I'm going to tally those values up, use the table, and get these values you can see. As I don't know the value for the O-double-O bond, I'm just putting X in there now, so that my total bond energy for the broken ones is 3231 plus 3x. So moving on to look at the bonds made, that's looking at all our products. We've got 4 COO bonds, 6 OH bonds, so I tally those up to get a value of 5998 kilojoules per mole. So using our enthalpy equation, so our total change in enthalpy is the sum of the energy required to break the bonds minus the sum of the energy to form the bonds, we can plug those values in here. So this number 1279 I've got from the equation, and these numbers 3231 plus 3x is what I've worked out from the bonds broken, and the minus 5998 is what the value I worked out. So you can see I've rearranged this equation to make x the subject, and I get a value of 496 kilojoules per mole for x. If you put negative 496, you would have only got 1 mark out of 3, but 496 gives you 4 marks.